Will we be computing with light? To understand computation with light and the concept of photonic computer chips, we must first delve into pre-existing forms of computing and the general direction of computational power that human technology has experienced since computers have existed. To start off, it might be helpful to understand processing power and the advent of CPUs or core processing units, which are generally referred to as computer chips. A CPU is the electronic circuitry that executes instructions comprising a computer program. The CPU performs basic arithmetic, logic, controlling and input-output operations specified by the instructions in the program. It's what allows programs to run and be displayed through our monitors, and more complex programs require more powerful CPUs. Faster CPUs allows a computer to perform more functions in a shorter amount of time. What can super-fast computers do that can help scientists and the general population? One example is the smartphone. Smartphones are a byproduct of computational research, which resulted in a change in how everyone lives on a daily basis. You get instant connectivity with anyone around the world, insanely fast devices capable of streaming media, making payments, among thousands of other uses all fitting into the palm of your hand. As for scientists, the advent of computers has contributed greatly to the fields of science. They have allowed for the collection and recording of vast amounts of data. They allow scientists to store information indefinitely and review it easily. Computers can be used to run automated tests and complete simple tasks, which saves time and makes work more efficient. A well-known machine that requires computational energy used in science is the robotic arm, which can be used to handle radioactive samples, perform delicate tasks, and anything that a regular arm could do, but more precisely. These robotic arms allow scientists to safely handle and test highly dangerous samples, which is one of the thousands of uses of computers and coding that can help scientists conduct their research safely and efficiently. So how does the general direction and progress of computational research look like? American engineer Gordon E. Moore observed and made the prediction that the density of transistors in a dense integrated circuit, like a CPU, will double every 2 years. So what is a transistor and why is it important? A transistor is kind of like a gate, which can be switched on or off in order to block or allow information to get through. The information sent or blocked by the gate is in the form of bits, which come in the form of zeros or ones. Multiple bits can be used to represent more complex information than the simple ones and zeros themselves. You can combine transistors to make what are called logic gates. A common gate called an AND gate will send an output of 1 if all of the bits sent through it are 1, and an output of 0 otherwise. Combining logic gates can give meaningful outputs like arithmetic functions. These functions allow for powerful computation by allowing for vast combinations of simple mathematics. While each logic gate performs very simplistic computations, having many of them can allow for the possibility to solve complex problems in astrophysics or to graphically represent movies using numbers to represent the activation of color pixels. As you can imagine, transistors are very important to the functionality of computers as they are the building blocks to allowing functions to be performed at all. They are what allow information to be processed and converted into a form factor that is easily recognizable to us either visually or in the background to allow everything to work smoothly. Gordon E. Moore's prediction of transistor density sets an expectation for the power of our electronics which so far has been very accurate. With the passage of time, our electronics are able to be smaller and more powerful than ever before. Now, this takes us to the question of when, if ever, will we be computing with light? Traditional computers use electrons, hence why we call our devices electronics, to send those bits of ones and zeros I was talking about earlier. The idea behind photonic processors is that electrons can only go so fast, which is approximately 100,000 meters per second across silicon, which is the material of choice in basically all processors. A faster particle does exist though, a particle we are all familiar with. Light travels at a speed of 299,792,458 meters per second, which is more than 2,997 times faster than the speed of electrons. The faster that the binary information can move, the faster complex functions can be computed, and the faster your computer is overall. A speed increase of 2,997 times normal would be a marginally significant breakthrough in computational research and make the processes we already do that many times more efficient. One example of how we use light to send information is fiber optics. Fiber optic cables use light as a means of connection to send info across the globe at light speeds. However, simply sending that information is fundamentally different from computing that information. At the end of the fiber optic cables, the light is filtered to output only electrons, which is then used to communicate information. As you can imagine, this is less efficient than if we were able to just use light without the intermediary action of filtering. The concept of photonic processors serves to address that issue of using light through and through in order to send and compute information. So what kind of research is being done to create photonic processors? Well, Light Matter is a supercomputer startup which has designed a wafer-scale chip using a special interconnecting fabric that uses light to boost performance while reducing energy usage. The light-based chip named Passage will allow arrays of other chips, including processors, graphics cards, memory, and AI, to communicate with each other. It also operates at an unprecedented speed compared to other existing solutions. Jelena Vukovic is a Stanford electrical engineer who has created a prototype photonic chip made of diamond. This initiative was to educate the world on how to make a light-based chip from a material nearly as hard as diamond, but far less exotic like silicon carbide. Like most chip-making materials, silicon carbide is a crystal, a group of specific atoms arranged in a consistent lattice. Vukovic's team made efforts to convert this crystal as a photonic chip. They removed atoms at strategic locations throughout the lattice. Each vacancy in the lattice created a subatomic trap that captured a single electron from one of the surrounding carbon atoms. In order to make the light-based chip work, the researchers sent a stream of photons through the lattice. Whenever a photon struck a trapped electron, the collision between those two particles sent a photon spinning off at a particular energy level, also called a quantum. MIT researchers have developed a novel photonic chip which consumes relatively little power in the process. The photonic chip could be used to process massive neural networks millions of times more efficiently than today's classical computers do. MIT researchers describe the new photonic accelerator as a chip that uses more compact optical components and optical signal processing techniques to drastically reduce both power consumption and chip area. This allows the chip to scale to neural networks several orders of magnitude larger than its counterparts. While commercial photonic chips may take some more time to hit the markets, the concept has been actualized and is being expanded on. Future supercomputers will indubitably use photonic technology and will perform the operations they already do, but much faster. Using photons instead of electrons will marginally increase computer speeds and allow scientists, researchers, and the general public to compute at unfathomable speeds and in higher volume. Just look at how much progress we've experienced over the span of 50 years. The same device you carry in your pocket is thousands of times more powerful than the computers on board the Apollo spaceship. Just imagine the changes we'll experience in the next 50. For comparison, an iPhone 6 could have performed the same instructions that the Apollo computers did, but 120 million times faster. The advent of photonic chips would move those numbers more than just a couple of decibels. Thank you.